So as always, I'll make sure to record this session in case you want to go back and review it a little bit later on. Make sure I got the right thing pulled up. There we go. All right, so like I said, the final exam posted earlier this morning, but is not due until the end of the day on Thursday, February 25th. So you still have 2 more days after today to work on it and get it turned in. But again, please, please, please do get it turned in by Thursday. Otherwise, I might not be able to accept it for a grade. And getting a 0 on your final would be not a good thing at all. All right. So like I said, today we're going to be talking about the kind of final physics aspect of this course that I wanted to go over with you guys. And that was the idea of these laws of motion. So they were invented by a guy named Isaac Newton, who is possibly who scientists consider as one of the smartest guys, one of the smartest scientists in history. Not only did he come up with these kind of super important ideas about physics, but he's also responsible for coming up with the super complicated math of calculus. He basically created a whole new type of math all on his own. So the things that we're going to focus on today are his laws of motion. Normally just called the first law, the second law, and the third law. So normally we'd spend 2 whole class periods kind of going over these and getting into each one. Since we don't really have that time here today, I'm just kind of focused on kind of the major important aspects of each law. So here is a very basic overview. The first law has to do with objects either remaining at rest, meaning staying still, or remaining in motion until some other force acts on them. The second law has to do with calculating force. It's equal to the mass of an object times that object's acceleration. And the third law has to do with action and reaction, how a force in one direction creates an equal force in the opposite direction. So I'll talk a little bit about what exactly each one of these laws means during our notes today. There is probably going to be a lot of stuff in the notes that you see me skip over. It's not because it's not important, but it's just because it provides a lot of kind of extra information that we just might not have time to get into today. So the first law of motion. There's a couple different ways that people like to write it out. One of them, the velocity of an object will remain constant unless a net force acts on it, which is kind of a fancy way of saying that an object at rest, meaning like standing still, not moving, will stay at rest, and an object in motion will stay in motion at a constant velocity, constant speed, unless or until they are acted upon by an outside force or an unbalanced force. It essentially means that something that is standing still will remain standing still unless something comes along and pushes it or pulls on it or shakes it or something like that. Same thing with objects in motion. If something is moving, then it won't stop moving until there's some sort of a force that is acted on it. So that's a lot of kind of science jargon for that first law. It essentially means that an object is going to keep doing what it was doing until it's acted upon by an unbalanced force. So if an object is sitting still, it'll remain sitting still. If an object was moving, it will keep moving. It takes force, it takes something acting on that object to change the motion of an object. So like my computer mouse right here that I'm using to move the little laser pointer all around the screen, when I put my computer mouse down on my desk, unless somebody comes along or the wind breaks the window in and blows on it, or there's an earthquake that shakes it, my computer mouse is going to sit and stay on my desk. It will not move. It is impossible for it to move unless some sort of outside force comes along and acts on it. So unless something interferes, unless there's this outside or unbalanced force, things will keep staying still. Same thing with if something is moving. If like you have a bowling ball going down the bowling lane or your car going along the road, it's not going to stop moving unless it's acted upon by some force. In a little bit, we'll talk about how friction and air resistance here on Earth slow down moving things when they're moving along the ground. But if you're, for example, if you're out in space and you like throw a tennis ball and the tennis ball's traveling at 10 meters per second, there's no friction and there's no air resistance in space, which means that tennis ball is going to fly through space at 10 meters per second forever until some sort of other force acts on it, until maybe it's pulled by a planet or it hits an asteroid or something like that. But if that doesn't happen, then it's just going to keep moving. It's going to keep doing what it was doing. So I mentioned a lot about unbalanced forces or outside forces. That's because it's still possible for objects to be sitting still, even if a force is acting on them. When things are sitting still, that just means all the forces are balanced. So all of us and all the objects on Earth are affected by the force of gravity. If there was a physics textbook for this class and you lifted your physics textbook off the table, when you let go, it's going to go down because gravity is pulling the book downward. Now, it's not going to go down very long, right? Maybe a couple tenths of a second before it hits the table. Gravity is still pulling the book down, but the table, the surface of the table, is resisting gravity and pushing the book back up. So the force pulling the book down is balanced by the force pushing the book up. So that's why this book is staying still, is because there are balanced forces going down and up, but no forces that are pushing it side to side or lifting it further up or down. So these guys are canceling each other out, basically, and causing there not to be any sort of motion happening with the book. And again, the first law says that if nothing else happens to this book, then this book is going to sit here forever and ever, till the end of time, if there's no other forces that come along and push against the book or exert themselves against the book in some way. That's what we mean by things at rest will stay at rest. They're not going to move unless something moves them. The first law is also called the law of inertia. And essentially just says that inertia is kind of a related term. It says that objects are resistant to changing a state of motion. Basically, inertia just means that the heavier that something is, the more mass an object has, the harder it is to change inertia. So if you have something really heavy that is sitting still, it's hard to get it moving, right? It's hard to like start pushing a boulder down a hill. Same thing with if something heavy is moving really fast, like you have a bowling ball that somebody just bowled full speed right in your direction. It's going to take a lot of energy in order to get that bowling ball to stop or to change the direction. It has a lot of inertia because it has a large amount of mass. So we know now that things that are staying still are going to keep staying still, and things that are moving are going to keep moving unless this outside force acts on them. And the bigger and heavier that something is, the harder it is to change its movement. And that's what inertia means. So things that are kind of common sense, but scientists like to put them into their own terms. So inertia is just, if something's really heavy, it's hard to get it to start moving. It's hard to get it to stop moving. And if it's moving, it's hard to get it to change direction. It all depends on the mass of the object. So like with these buckets right here, we got an empty bucket and a bucket that's full of sand, which is pretty dense and can get pretty heavy if you have a lot of it. Inertia says, well, the first law says that if no other forces act on these buckets, then they're going to stay still and not move. Inertia says that this bucket is going to be easy to move, and this bucket is going to be harder to move. So because this bucket is heavier, it has more mass, and so it's harder to get this bucket to start moving than this one. On the flip side, if both of these buckets are swinging really widely to and fro, I'd rather be hit by the empty bucket than the full bucket. Because the empty bucket, it's going to take less energy for me to stop it with my body. So it's probably not going to hurt so much. The filled bucket is heavy. It's going to have a lot of inertia, and you're going to need a lot of energy in order to get it to stop. So it's probably going to hurt pretty good if that knocks into you. So inertia just means that heavier things are harder to move, or if they're already moving, they're harder to stop or change direction. More stuff about inertia. So yeah, if an object has a large inertia, large mass, if it's moving, it's hard to get it to slow down or speed up. If it's at rest, it'll be hard to get it to start moving, and it'll be hard to make it move in a different direction. So like I said before, when you're in space, you don't have any friction or air resistance. So if an astronaut in space throws a rock, the first law says that the rock will keep moving in a straight line at a constant speed. There's no other forces that are acting on the rock to slow it down. So it's going to keep going at a certain speed until it encounters some other force. So here's one of my favorite examples of inertia, and it's also the reason why it's very important to wear seatbelts. So this car and this person are both traveling at the same speed, right? They're traveling down the road at, let's say, 40 miles an hour. The car hits this brick wall. So it comes to a stop very, very, very quickly because this brick wall put a big force on the car to make it stop. The person in the car did not hit the brick wall. They don't have anything besides a steering wheel and maybe the windshield in front of them. They haven't actually hit anything when their car hits the wall. So the law of inertia says that an object in motion, like our little dude here, wants to stay in motion unless a force acts on it. So when the car stops, this dude keeps going because your body is still moving at 80 kilometers an hour, which in this case would be like 50, 55 miles an hour. So your body, even though the car stopped, your body still wants to keep moving. And if you're not wearing your seatbelt, that's why people get thrown out of their car windshield. And that's why seatbelts are important. Because when you're wearing your seatbelt, that exerts a force on your body. Your body tries to go forward, but your seatbelt exerts a force and holds you back. Yeah, it might hurt and you might get a bruise and you might break something, but it's a lot better to exert that force than to exert the force of the pavement over here on your face. That is not good. So all of this extra movement from our person here is due to inertia, due to that first law of motion. Things in motion will keep in motion until they are acted upon by an outside force. For the car, that outside force is this brick wall. But for this person, that outside force is probably going to be the asphalt over here on the other side. That's what's going to stop them from traveling at 80 kilometers an hour. Same kind of example right here. If you're like balancing a rake on top of your wheelbarrow and you're going along and the wheelbarrow hits a rock and its forward motion stops because of this force, the rake doesn't have a force acting on it, so it'll keep moving forward and fall off of your wheelbarrow. The object in motion wants to keep going in motion. So earlier when I was talking about like the astronaut throwing a rock in space, the reason why I said it in space is because on Earth, when things move across the ground or move through the air, there are lots of forces that are acting on them. There's the force of friction, which is a force when things rub against each other. There's the force of gravity, which is what pulls objects down to the ground. And then there's also, it's not mentioned on here, I don't think, but there's also the force of air resistance. So as you're going through the air is exerting a force back on you. That's why when you're like driving down the highway, if you stick your arm out the window, you can feel the air pushing against your hand really hard. So all these forces are what affect the motion of things here on Earth. So friction is the big one. It's when two things are moving across each other. So it's the reason why if you let your foot off of the gas pedal, your car will eventually come to a stop. If you roll a ball around the ground will eventually, or the ball will eventually come to the stop. If you are riding a bike and you're pedaling, and then you let go, friction is what slows the bike down. So the friction of your bike tires on the ground, on the asphalt, causes the friction force, which is usually in the opposite direction that you're traveling. So there's friction between your car's tires and the ground. There's friction between your bike's tires and the ground. There's friction between a soccer ball or a bowling ball or a tennis ball and the ground. And that friction force is what causes things to slow down. It's applying a force in the opposite direction from where the person or that object is traveling. Some more things about friction, momentum. We're not really gonna talk about. It's essentially kind of related to inertia, but it also has to do with how fast things are going. We're not gonna worry about momentum. Blah, 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 blah. Okay. So before we move into the second law of motion, does anybody have any questions about the first law of motion, about remaining at rest or remaining in movement or inertia or anything that we've talked about so far?
No.
All right. So main things to remember about the first law is just that objects at rest will stay at rest, or objects in motion will stay in motion until they are acted upon by some sort of outside force. Whether that's a wall stopping them from moving, or friction causing them to slow down, or a person coming along and hitting them. Those are the sort of outside forces that will cause a change in something's rest or motion. So the second law of motion is a pretty simple one. It has to do with the force that is exerted by objects that are moving. And the second law simply states that force equals mass times acceleration. So the force that has been exerted on an object can be calculated by the mass, how heavy an object weighs, and an object's acceleration, how quickly is it speeding up or slowing down. So acceleration is simply a measurement of how fast is something either speeding up, getting faster, or slowing down. A low acceleration means that things are really slowly going from not moving to moving fast. A high acceleration would mean that things are very quickly going from stopped to moving really fast. It can also work for deceleration, or going from really fast to stopped over a short period of time or a long period of time. So F equals m times a, or F equals ma. Force equals mass times acceleration is the formula for the second law of motion. Force equals to mass, so the weight of something, times acceleration. How fast is it speeding up or slowing down? So there are a couple different ways we can think about the second law. One of them is that if you apply more force to an object, it accelerates at a higher rate. So F equals ma, which means that if mass stays the same, so in this case, when this dude's pushing this cart, the mass of the cart is the same each time, right? It's got the one little box and a lot of empty space and some little wheels. The mass isn't changing, which means that if our force goes up, so we put more force, then our acceleration is going to go up. So we put more force on the same thing, it's going to move faster. It's going to increase speed very quickly. So that's one way to think about the second law. Another way is that if you increase the mass of something, you'll need more force in order to accelerate that object. So if this wagon is at rest and it has one of these, I don't even know, one of these little stone, let's say, objects on it, then it might require a small amount of force to pull it and get it started accelerating. But if you increase the mass, then you're going to need to increase the amount of force needed in order for that same acceleration. So if the mass goes up, then the force will have to go up in order to compensate. So to get the same acceleration with more mass means you got to put in more force. You can also use it to calculate how much force an object is likely to have. So when you're playing soccer, you know, you're kicking a soccer ball around and you're using your foot to impart a force on the ball. And so if you know how heavy that the ball is, its mass, and you measure how quickly that ball accelerates after you kick it, you'll be able to measure how much force you put into kicking the ball. So you'll be able to calculate how much force did it take you to move a ball of that size that quickly with that much acceleration. All right, so that one is a pretty simple one, but it's basically just describing the relationship between force, mass, and acceleration. If you put more force into something, then it'll cause the acceleration to go up if the mass is the same. If the mass increases, then you'll have to put more force into it in order to get it to move. Or if you put the same amount of force, you'll have a lower acceleration, right? If you put a certain amount of force on a object that doesn't weigh very much, it'll probably go very quickly. If you do that exact same amount of force on an object that is a lot heavier, it'll go a lot more slowly. Again, it's kind of all things that make sense in your mind if you think about it a little bit, or if you think about kind of your life experience. But this is how scientists have put it into measurements, into ways of calculating things like force and acceleration. So Newton was the first guy who figured out that force and mass and acceleration are all directly related to each other. All right, the second law is always a pretty quick one to talk about since it's really only kind of explaining that F equals ma equation. But is there anything that anybody has any questions about? Anything about the second law that you want a little bit more explanation
on? No.
All right, great. Thanks, Dewey. All right, so the third law is probably the most complicated out of the three. It's often known as the law of action and reaction. And essentially what it means is that when an object exerts a force on the second object exerts a force on the first one that is equal in magnitude and opposite in direction. So the second object exerts an equal force in the opposite direction. So this one is kind of hard to just explain using words. So I like to try and use a lot of examples to kind of show how exactly this works. You often hear it referred to a lot of times as for every reaction or for every action, there is an equal and opposite reaction, meaning for every force against something, there is an equal force in the opposite direction. So one good example of how this third law works is if you think about a rocket ship, right? Rocket ships have these big engines on the back of them that are used to, if they're on the ground, they're used to push the rocket up into space, or they're used once they're in space to push the rocket forward in space. So the way that a rocket engine works is that there are all these chemical reactions that happen inside the rocket, and it basically creates a ton of downward or backwards force, right? They have this really intense kind of exhaust, this really intense, like you've seen the video of like the flames and stuff shooting out the bottom of the rocket, all the smoke coming out. That all is going out the bottom of the rocket. So there's all these gases that are very forcefully being pushed out the back of the rocket. When that happens, it causes the rocket to be pushed forward. So this exhaust flow going out the back of the rocket causes the rocket to be pushed forward or be pushed upward if it's like sitting on the launch pad. So the rocket is moving in the opposite direction of where all of its exhaust is going, right? The exhaust is going out the back, but the rocket is being pushed forward. That is what the third law is all about. For every action, as the exhaust is pushed out the bottom of the rocket, there is an equal and opposite reaction. The rocket is pushed upwards by this backward flow, or pushed forward by this backward flow. Oh, there we go, yeah. So we have all of these intense hot gases from fuels being burned inside of the engine, and they escape out the bottom of the tube down here. So as the gases move downward and exert a force downward, there's an equal force that's then exerted upward on the rocket ship itself. So as the gases move down, the rocket shoots up. Equal and opposite reactions. So an equal amount of force in the opposite direction. All the gases coming down and out cause the rocket to be pushed up. It's the same idea if you have like a balloon that you fill up with air, go, right? And so the balloon is all stretched out and you're holding on to the little thing on the bottom. And then you let that go and it goes, and the balloon shoots off, right? All the gas, all the air that was inside of the balloon is being pushed out, being forced down out of the balloon. But the force of that air coming out the little, I don't even know what that, the little tip, the bottom part of the balloon, the air being forced out downwards makes the balloon shoot off in the opposite direction. And that's because of the third law of motion. The same thing is even working for things that are standing still, like this person sitting in a chair, or the physics textbook example that we looked at in the first law. Your body, or that book, is exerting a downward force due to gravity, and this chair, or that table, is exerting an upward force based on the fact that it's like a solid piece of material, so you can't just go straight through it. So there are these opposite forces interacting when you're sitting down on something, or when there's a book or a mouse or a phone laying down on a table or something like that. The downward force of the gravity on the object is being matched by the upward force of the surface of that object is sitting on. Another good example is how birds fly. So birds have these wings, and they move their wings through the air, and as they push on the air, that's what allows them to fly. So birds push their wings down, right? And you can see that in the little GIF here. The bird's wings are going down, and whenever that happens, the body of the bird goes up. Because as the birds push down on the air with their wings, the air pushes up on their wings and body, and that's what gives them their lift, their ability to fly through the air, is because their wings are pushing on the air, so the air pushes back on the wings. Another good example that I like to think about for this a lot is if you're ever on like a skateboard or something, or like a rolly chair, like I have here for my office chair. If you're standing on a skateboard, or you're sitting on a rolly chair, if you're up against a wall and you push against the wall, your push is going, and for you guys looking at this camera, the push is going forward, right? I'm pushing towards you when I'm pushing against, if I was pushing against my computer here. But if I did this, if I pushed towards you on my computer, I would be pushed backwards. And if my dog was laying here right behind me, I could push against my desk forward, and my chair would roll backwards, all due to that third law of motion. As I push against the desk is pushing back on me, and that's what's causing me to roll backwards. Or as you're on a skateboard, when you push against the wall pushes back against you, and you'll roll in the opposite direction. Balloon example I mentioned earlier, as air rushes down out of the balloon is forced up into the air. As you're nailing something into like a wall, you're not going to just put the nail in exactly on the first try, right? Because while the hammer is putting force against the nail and against the wall, the nail and the resistance from the wall is putting force back on the hammer. So equal and opposite directions. Another one of my favorite examples involved if you're ever going to go step off of a boat or something like that, right? Or if you go think about the skateboard from earlier. If you're standing on like the edge of the skateboard and you're going to get off, or you're on a boat and you're getting ready to get off back onto land, or you're going to jump into the water, with your foot, you push down on the boat in order to go forward, right? That's how we walk. We put our foot down and then go forward. But if you ever do this, especially on the edge of the boat, or if you're on like a skateboard, you're probably going to roll forward and hit your face flat on the ground or flat on the water. And that's because the boat or the skateboard is going to move back in the opposite direction. So while you're pushing to go forward, you're also pushing against this boat or skateboard, which is going back in the opposite direction. Same thing with if you're swimming, right? If you want to go that way, you don't do that by forcing your arms that way to try and move, right? You might put your arms out in front, but then you push the water backwards, and then you push the water backwards, and you push the water backwards. As you push the water back, the water exerts a force on you and pushes you forward. So we have these equal and opposite forces. When you have an action force, there's some sort of reaction force. Pushing the water backwards causes you to go forwards. Pushing the boat or the skateboard backwards causes you to go forwards. Hot gas shooting out the bottom of a rocket ship causes the rocket ship to go up. All of this is due to that third law of motion. Force on an object will be met with an equal and opposite force. Action and reaction. Let me see if there's other really good examples. Wall, dive in the raft. That pretty much covers most of the things. Throw a ball like a tennis ball or a bouncy ball or something. You throw it against the wall. The ball puts a force on the wall, right? It's going to hit the wall and collide. But as it does, thanks to the third law, the wall puts a force on the ball, which causes the ball to bounce back off. So that is our third law of motion. When you exert a force on an object, or when an object has a force exerted on it, it will exert an equal force in the opposite direction that that initial force was placed. So we have these opposing forces that cause all sorts of different movements and reactions when these forces collide with each other. But it's all due to this balanced action and reaction. For every action, for every force, there's an equal force in the opposite direction happening against it. All right, so does anybody have any questions on our third law of motion here? I've tried to make sure to hit on a bunch of different examples because I know this one is probably the trickiest one to kind of wrap your head around. Leah seems good. Anybody else have any third law questions?
The formula is same. The second law.
Yeah. So if you wanted to calculate exactly the forces involved, then you could use the formula from the second law. So you could see, okay, when they collided, the first object weighs this much and it had this change in acceleration. So what kind of force was exerted on it in order to get it to slow down or stop? So yeah, exactly. If you wanted to calculate the forces that were involved, you could use the second law in order to do that.
Okay.
Awesome. Great question. Any other questions, not just about the third law, but any of the laws that we've talked about today? Either inertia and remaining at rest or motion until acted upon, F equals ma, or action and reaction. Any questions on the three laws of motion? All right. So because of all the craziness from the past couple weeks, I tried to make it, and since you guys are going to be working on the final this week, which does have a couple of laws of motion question on it. So definitely feel free to refer back to these notes or refer back to this video if you get a little bit stuck on some of those questions on the final. But there will be at least 2, maybe 3 questions related to laws of motion on the final. So the assignment for yesterday was that simple one about what kind of topics do you want to review. The one from today is another simple one about that second law equation. And then Wednesday and Thursday's assignments are just kind of basic end of the year wrap-up assignments about things that you found interesting about this course or things that you thought worked really well or maybe didn't work so well in terms of how the course was set up. So pretty simple questions that you should be able to do and not have to think about too much. So instead, you can focus on making sure to finish up your final exam. Again, your final is due by the end of the day this coming Thursday, the 25th. So please take a look at it, start working on it, reach out to me if you have any questions on it. On Thursday, we'll be doing a whole course review of hitting as much stuff from the last term as possible. So if you do get stuck on any of the different parts of the final, then please come on Thursday and maybe I can help get some of your questions answered with that review. All righty. Anybody have any final questions about anything before we wrap things up here for today?
No question.
Me too.